What is the difference between an optical microscope image and an electron microscope image? I've prepared two samples that clearly show those differences. The first one is a fly head. The second one is a small fragment of an Intel CPU from 2004. The optical microscope used in this video is the Olympus DSX 1000. It is a high-end metallographic optical microscope. Its price is above $20,000. It is mainly a very good optical microscope. The raw image quality is comparable to standard high-end optical microscopes. The second instrument is a scanning electron microscope, Fey Helios Nanolab 650. It is about 10 years old. At the time of its purchase, it was one of the best microscopes available on the market. Its price was around $1 million. In this video, I will focus only on the most basic scanning electron microscope function, imaging using secondary electrons. Both microscopes are located in the laboratory of the Center for Microelectronics and Nanotechnology at the University of Rzeszów in Poland. Let us start with the optical microscope. The sample is already placed under the objective. It is mounted on a custom 3D printed holder that allows easy manipulation of samples mounted on a standard aluminum scanning electron microscope stubs. We start with a 5x objective, which together with the camera optics gives about 70 times of total magnification. On the screen we can see the entire fly head. This is the lowest magnification available in this configuration. If I focus on the tip of the fly head, everything below becomes blurred. This is a typical feature of optical microscopy. Limited depth of field. Sometimes this effect is useful, but in most cases we want the entire image to be sharp. Now I switch to 20x objective, giving about 270 times of magnification in total. At this point, it is already difficult to observe the sample because the depth of field is very shallow. Only a very thin layer is in focus. One possible solution is to take a series of images, each focused at a slightly different height, and then combine them using an algorithm that keeps only the sharp regions. This technique is called focus stacking. This microscope handles it automatically. I only have to set the lowest and the highest focus point, click Start and wait. The result is an image with a very large depth of field, where all important details are sharp. In general, higher magnification means shorter working distance and shallower depth of field. There are special microscope objectives that provide a longer working distance, for example 1 cm instead of 0.5 mm, at the cost of slightly reduced resolution. In the case of the fly head, using a standard 50x objective is impossible. When I try to focus, I accidentally touch the fly's hairs, which causes the entire sample to move. This could even damage the objective. Instead, I use a special long working distance 50x objective, which allows observation of the fly's eye at about 700 times magnification. This is the final focus stacked image. Now let us move to the second sample, a fragment of an Intel CPU from 2004. I made a separate video about this processor and its 90 nanometer lithography process. However, Most structures visible here are larger than the resolution limit of an optical microscope. The resolution limit of optical microscopy is around 200 nanometers, which is approximately the width of a single interconnect line in this processor. We should not expect to see individual metal lines clearly. And indeed we do not. Physics works exactly as expected. At 700 times magnification, the image is still acceptable. At about 2000 times magnification, achieved using the internal optical zoom system and camera optics, the optical microscope is already at its limit. Now we switch to the scanning electron microscope. First, the samples are loaded into a special holder. Here you can see the inside of the SEM chamber and its internal modules, all focused on the central region where the sample will be placed. After loading, the chamber is pumped down. Achieving the required vacuum takes about 10 minutes. The sample must be completely dry so that no gases evaporate into the chamber. It also needs to be at least slightly conductive. Pure plastics or rubber cannot be imaged easily. I will explain why and how to solve this problem in a separate video. Now let us compare the fly's eye images. The first obvious difference is color. Electrons do not see color. SEM images are always black and white, or more precisely monochromatic. They represent the intensity of interaction between the electron beam and atoms in the sample. Another important difference is acquisition time. Taking an SEM image takes much longer than in optical microscopy. Depending on settings, it can take from a few seconds to several hours. The depth of field in SEM is dramatically larger. At a magnification similar to 270 times in the optical microscope, the entire eye is in focus. No focus stacking is required. Do not rely on the magnification value shown on the screen. It is only correct for a specific screen size. I manually adjusted magnification to match the optical microscope images. At 700 times magnification, we can see dirt, wrinkles and fine details on individual eye segments. Further magnification is limited by the poor conductivity of the sample. Now let us move to the processor sample. At low magnification, differences are subtle. At around 700 times, images are still comparable. But around 2000 times magnification, the optical microscope struggles while the electron microscope is just getting started. Here we reach twice the maximum of useful magnification of optical microscope. And finally, the maximum magnification I achieved for this sample about 20 times higher than the optical microscope limits. The theoretical resolution of this microscope is about 0.1 nanometer. I've never achieved this value. However, with a well-prepared sample, for example gold nanoparticles on carbon, late at night when vibrations and electrical noise are minimal, I can approach about 2 nanometers resolution. This corresponds to magnifications of 500,000 times to 1 million times. For comparison, the diameter of a hydrogen atom is about 0.1 nanometers and a gold atom is about 0.3 nanometers. We are very close to seeing individual atoms, but for true atomic imaging, other types of microscopes are used. I will talk about them in the future. See you in the next video, this time maybe faster than 5 years later.